Alright, it's 8 a.m. now, so I'm probably gonna sleep after this. But this is the fifth part to systems of linear equations and matrices, which is the first part of linear algebra. So, this time we're looking at elementary matrices and a method for finding the inverse of a matrix, right? And this is some quite cool stuff. So, we're looking at elementary matrices. This is gonna look really silly and goofy, right? But let's say, okay, matrices A and B are row equivalent, all right? We're defining a new term here, row equivalent, if either can be obtained from the other by a series of elementary row operations. If you remember from the first part, that's like when you do something like, or you multiply this row by 3, or you switch these two rows, or you add this much of this row to that row. That kind of stuff, right? If you can just, based on those transactions, you can go from A to B, they are row equivalent. Now, a matrix E is called an elementary matrix if it can be obtained from an identity matrix after performing a single elementary row operation. And so that means like the matrices like this. Like here you have the identity matrix 2. You multiply the second row by -3. This is E, this is elementary matrix. Here you can swap the rows of R2 and this is actually R4 of the identity matrix of size 4 to get this shape, right? Here you can add 3 times the third row to the first row, as you can see here in the identity matrix of 3. And even crazier is you can just do this. You multiply the first row by 1 in, that's not R2, that's supposed to be I2. But yeah, so this like very, very rudimentary basic stuff. It's just one move away from the identity matrix. And you might be wondering like, what the heck is this for? Well, it's for this. If you in theory, if you multiply any of these elementary matrices to a regular matrix, that regular matrix will be equal to like the result of that will be equal to performing that elementary row operation on that matrix. So it'll be like, so yeah, if you have EA where A is a regular matrix and E is something like this, add 3 times R3 to R1 in the identity matrix, it will be as if you added 3 times of the third row to the first row in A. So that's how that works. So lucky us, we have a way to like test this out. And so we can put, we can combine these together, all right? So if we do EA, that would be, this has, what is it, 3 by 3. This has 3 rows and 4 columns. So that would be, I don't know, right? Okay, I'll cut back. All right, so now you can see this, and if I just perform each of these things, which I'll do off camera again, you'll see how it works. So I'll just do the first one, visible. If I do EA11, that will take the row of E and the column of A. So that would be 1 times 1, and it's 0, 0, so I can move on to the next thing. So I'll just finish all that up. Okay, so after putting all this together, we are able to get this matrix, which is equal to 1, 0, 2, 3, 2 minus 1, 3, 6, and then 4, 4, 10, 9. Bam. All right. And what you'll notice is that the first 2 rows look like the same. They're the same as that, right? And this last row is the same as taking this multiplied by, like, because this is this elementary row operation, this one, it adds 3 times. It's different. Okay. This one adds, what is it? Shoot. This is, it adds 2R3. It adds 3 times the first row, right? So that's 3 times the first row to the third row. And we can see the same thing here where it's 1 times 3, that's 3 plus 1, we get 4. 0 doesn't affect it, so it stays as 4. 2 times 3, that's 6, plus 4, that's 10. 3 times 3, that's 9, plus 0, that's 9. So we can see, you know, just by doing this multiplication, doing like the E, we get, you know, the value, we get this row operation performed on A by using this elementary matrix. So that's kind of the idea behind elementary matrices, right? And we can see here, every elementary matrix is invertible, right? That's because, you know, it's just one step away from the identity matrix. If we have 1, 0, 0, 1 here, you can like do something to swap it, and you can just swap it back. So it's easily, you know, invertible. If you change this to be like times 10, you can just times 1 over 10 and then it goes back to normal. So that's why, you know, they're all very easily invertible. And next, its inverse is the opposite of the elementary row operation conducted on it. Yes, we talked about that. And the inverse is also on the elementary, is also an elementary matrix. And because if you remember the definition of an elementary matrix, it's just a matrix which is one step away from the... Shoot, there's a freaking window something. Anyways, it's a matrix that's one step away from the identity matrix. And so, you know, if we have that thing again where this is the elementary matrix has like multiply R2 by 10, if we do the same thing, divide R2 by, like, multiply R2 by 1 over 10, you know, you can have this. And that's also, like, these are both elementary matrices, all right? Even though this is like the inverse of this, they're both elementary matrices. So bada bing, bada boom, you know, that works. So moving on, this is something very, very interesting, and it's called the Equivalence Theorem. And it's a way of connecting like the things in the past, like 5 parts that have been discussed, and just linking it all together. So this states that if A is a square matrix, then all of these statements are connected. So either all of them are true or all of them are false. So they're all linked together. And so the first one is that A is invertible. That means that the inverse of A exists, right? The next thing states that like A, this is, if you remember homogeneous linear systems, if like this states that the A in a homogeneous linear system has only the trivial solution, which means like everything, all the unknowns equal to 0, and there's no like there's no free variables, right? Freaking yeah. And then this states that the reduced row echelon form of A is the identity matrix, right? So it can be reduced all the way to identity matrix with no weird gaps or 2s and 3s around, right? And lastly, A is expressible as a product of elementary matrices. And that means that you know how like we talked about elementary matrices, you have like the I that doesn't say anything. Okay, I'll get back to that later. It's better explained afterwards. So this is all just the proof, right? So here we can see like, if A is invertible, then if you have, you know, this kind of homogeneous linear system, you multiply it by the inverse to the left. These cancel each other out. It's the inverse matrix. This is kind of just here, but you know, since this is the inverse matrix, this has to be 0 now, you know, since this is 0. So bada bing, bada boom. That proves that only the trivial solution exists. So here, if we have our homogeneous linear equation and we assume that only the trivial solution exists, we can see like, we can just simplify this step by step. All right, I had a limited amount of space here, but we can simplify this just to the identity matrix. You know, it's just ones, 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 and zeros. Because if we assume that there's only the trivial solution, there's no like non-trivial solutions, there's gonna be no row at the bottom here. There's just all zeros, right? We can forget about that. So next, if it can be an identity matrix, this is what I was talking about, it can be represented with a bunch of elementary rows, because it is through the elementary matrix, because each like element you convert it to the identity matrix using elementary row operations, and so each elementary matrix applies those elementary row operations. And so here, by just adding a bunch of elementary matrices, it's the same as putting doing a bunch of elementary row operations to A to create that identity matrix. And lastly, if A is a product of a bunch of elementary matrices, as we set up here, each elementary matrix is invertible, and thus if you go backwards, A can be inverted, which is explained further in the next page, where we talk about a method for finding a method for inverting matrices, right? So here, look, this is quite crazy. If you can turn A, we already know you can turn A into the inverse matrix, right? By putting a bunch of these things. So if we just multiply the right of both sides by the inverse of A, we can put it here with the identity matrix, and we can put it here. These two can clump together to create the identity matrix. While this, anything multiplied by the identity matrix is itself. So this goes back to the inverse of A. So from this, just that simple operation, we have converted like how to turn A into the identity matrix into how to get the inverse of A from the identity matrix. You legit just like swap the locations. So that's very simple. So a way to like do this intuitively is to just concatenate them. So put A and I side by side. You can put that line. And so each time you perform a row operation onto A, it's automatically reflected in I. So there's a good example we can try here. This is the goal, and this is the A we have. All right. So let's try to convert this into. Let's try and get this to work. So let me just set it up. All right. So now do we have this? We can just solve it normally. So R2 based on Gauss-Jordan elimination. We can say R2 is R2 minus 2R1, and R3 is R3 minus R1. So if you put that together, that will turn into this, where we've subtracted 2 of this, we've subtracted 1 of this, and it reflects here. All right, we did the same thing here. So now we can say like R3 is R3 plus 2 R2, and let's see what that gets us. Okay, and now we're here. It's quite simple. Let me just like multiply this by -1. I don't have a lot of space left on the page, so I'm just gonna squeeze that in. Now I'm just gonna do the Jordan part and like add it up. So this would be, is that -3? Yeah. So this would be R2 is R2 plus 3 R3, and then R1 is R1 plus what would be, minus 2 R2, and what would be minus 3 R3, and I think that should give us our answer. So I'll just calculate it off screen. And so this is what I got, where we have the identity matrix here, I3, and bada bing bada boom, this matches up with this. Hey, that works out. So that's pretty cool, and that's how you can find the inverse matrices. and this works for like all sizes of matrices, of square matrices. I mean, squares are the only thing to have inverses, so all matrices, without just having like the 2x2 matrix. And I think there's one last thing here of like when things don't really work out. So this is this is a matrix, and let's try and find the inverse, right? So we're gonna start by, okay, let's just rewrite it, right? 1, 6, 4, 2, 4, minus 1, minus 1, 2, 5, and we'll have the identity matrix next to it. And then do, start with, so R2 is R2 minus 2 R1, R3 is R3 plus R1. Just do this, and so that would be, all right, so I'm back here, boop, and then that is what I got. And then we'll continue the thing here. Okay, so shoot, let's do this first. R3 is just R3 plus R2, cancel that out. And I'll just show you before I simplify R2. 1, 6, 4, 0, minus 8, minus 9. But this turns into 0, 0, 0, right? And it doesn't matter what we have here. We see this, it's dead. All right? Remember what I said in the last chapter, where anything with like a full row or a full column of zeros can't have an identity matrix. Yeah, we mentioned here. See, since there was this column here, we can't have that identity matrix because it won't turn into 1, 1, 1. So you can't get that inverse either. You can't get the identity matrix, can't get the inverse. Very much here. We're actually looking for the identity matrix. You can't get the identity matrix, so of course you won't be able to get the inverse. But yeah, that's everything for this topic. So yeah, chill. This is Scooby.